Okay, let's start. So, good morning, everybody. Thanks for attending this workshop. So, we organized five workshops to allow open call to experiments to present their realizations and the solutions they developed in the framework of FF4EuroHPC project. So this is the second workshop, and we will include this agenda. So we start with this welcome, an introduction made by my colleague Tina. Then we will have a presentation by Kevin Charpot and Marco Zanichelli from AYRO concerning a numerical tool for the optimal design of wind-assisted propulsion technology. Then Dimitris Lampropoulos from FEACOMP will present high-fidelity modeling for small wind turbine. Then Eduardo Perez from BSc will present an HPC-based virtual platform for low emissions hydrogen-based technologies for industrial combustors. Later, Georg Scheger from Tkconsult and Erwin Schnell from AYRO will present a solution solving ambitious challenges in high-end wastewater treatment using HPC with safety simulations. And at the end, João Vidal from Soprefa will present high performance computing for profile extrusion. So a session of questions at the end of each presentation will be is planned, and you can shake your hand or ask the question using the question section for this webinar. So I let the floor to my colleague Tina to introduce the project.
Yeah, hello, good morning.
Hi,
so I guess you should see my screen now.
Yes,
exactly.
Good. So hello, welcome everybody to this webinar. My name is Tina Mark and I'm the FF4EuroHPC communication lead. And before we are heading to the success story presentation, I will give you really a brief overview on this project. So the FF4EuroHPC is a H2020 R&D project. It's coordinated by HLRS and supported by 5 other partners. We have Arthur, Sesga, Cineka, Scapos, and Teratec. And actually, this project is all about promoting the use of HPC for business. So how can industry actually gain innovation and benefits by using HPC and other related technologies, such as artificial intelligence, machine learning, deep learning, and HPDA for their business. But furthermore, we are also facilitating the access to HPC-based infrastructure and also the experiment partners who provided the success stories can also gain the access to some of the EuroHPC machines. Furthermore, actually, as I mentioned, we are promoting the use of HPC in business, but it's also the case of innovation. So how can actually industry be more innovative when using the technology? And lastly, by offering 2 open calls, we were providing an effective mechanism for SMEs to lowering their barriers when entering the new markets and offer them the opportunity to exploit new business opportunities. So 2 open calls were offered within the project, and we were targeting actually the really highest quality experiments that were provided by Agile SMEs. So in total, we found that 42 experiments which were selected and they are including 132 partners from 22 EuroHPC member states. On your right-hand side, you can see the map. So all these, let's say, darker blue colored countries are part of these experiments, and we're really proud of to cover this geographical, let's say, aspect. And I would also like to emphasize that 62% of all partners are small and medium-sized enterprises. So experiments and experiment partners, of course, addressed different business challenges, which they were solving with the help of technology, with the focus on HPC, in various application domains and sectors, but most of them, so 57% of them, were covering manufacturing sector. So experiments actually have a duration up to 15 months, and after they were successfully concluded, they are resulting in so-called success stories. So this is a story that highlights the business benefits and inspires the industry community. So it's all about describing how the experiment partners were addressing the problem, what kind of solution they used, and how they developed and addressed the problem, and after all, what kind of business benefits and of course impacts do they gain during the experiment. And we are really happy to say that the first tranche was really successful. We have 16 success stories. All of experiments were successful. They are already produced. You are kindly invited to use our project website. You have the QR code here. My colleague Lucille already provided you also the link to the website in the chat. And you can search for the success stories and explore a bit through really different, I would say, industrial sectors. We also provided the first success story booklet. It's also available on the website in the digital format. And I would like now to invite you, of course, to follow us on these social media channels where we are providing more information about success stories, HPC-related events, and other HPC-related content. And also, we will soon inform you about new success stories, which will be presented during the workshops. So this is the second one, and 3 more are coming. So
thank you for the introduction. Today with Marco from Tkconsult, we are going to present the project C-Motion, a numerical tool for the optimal design of wind-assisted propulsion technology. The consortium is composed by AYRO, Politecnico di Milano and the DAER department, Cineca, Tkconsult, and UC. The outline of the presentation. So I will start with the context and the objectives. Then we will present you the work done during this project. And I will end with the main achievements, the expected impact, and the conclusion. First, about the context. So today, most of the world trade is carried by the shipping industry, and we expect it to double by 2050. The shipping CO2 emission will increase to 17% of the world transportation CO2 emission. Strong regulation are enforced by the International Maritime Organization and impose 70% of CO2 reduction. In this context, the maritime sector is looking for new technology. So we can identify 2 main ways. We can work on the energy saving devices and on the wind propulsion system. The wind propulsion system can save up to 45% of CO2 emissions. Within this context, AYRO is developing a new wing sail, so the ocean wing system. It's an automated 2-element wing sail, twice as efficient as a traditional sails. It can turn 360 degrees around the main axis, and it has a secondary element, the flap, that can be orientated to adjust the camber and optimize the performance. In case of bad wind condition, the sail itself can be furled. So the ocean wings are safe, reliable, and competitive. The ocean wing systems aims to be installed on any kind of vessels. You can have 2, 4, 6, or even 8 ocean wings on a ship. Okay, so the motivation. First of all, the SimOcean project aimed to address environmental and economic challenges in ship decarbonization. AYRO focused on optimizing ocean wings technology and expanding its customer base across ship types. From wind conditions, speed and angle, the question is, how must be the orientation of each ocean wings to get the best performances? However, AYRO faced challenges in efficiently evaluating different ocean wings configuration due to limited expertise and computing resources. This is why a consortium partners with Polemy, Cineca, Toolspolz, and UC collaborated to provide CFD simulation, HPC resources, workflow automation, and surrogate modeling techniques. The objectives include developing and optimizing AYRO's WASP systems, leveraging advanced CFD methodologies and HPC techniques, enhancing computational capabilities with HPC resources, creating user-friendly tools for ship designers, and improving ship performance and emissions reduction in the maritime sector. The challenges include computational complexity, integration of multidisciplinary expertise, and real-life industrial applicability. These challenges are overcome through comprehensive and interdisciplinary approaches and effective collaboration among partners. So here is the overall approach of the project. So AYRO provides the inputs with the ships, the ocean wings configuration, and the wind conditions. Then a 2D workflow was developed by Polemy, and the automation development was made by Cineca. A dataset is created for response surface methodology that is used in an optimization process based on Bayesian optimizer developed by Toolspolz and UC. This finds the best orientation according to an objective function. Finally, a 3D validation is performed, and at the end, we have the contribution of the ocean wings to the thrust of the ship. So I will start with the CFD part. So Polemy developed a 2D workflow based on OpenFOAM technology. It developed multi-step meshing. So as we have multiple wings and knowing in advance the number and the position, we generated background mesh. Then we generated a mesh for the wing profile. So the main and the secondary wing profiles of the ocean wings are oriented accordingly to the geometry. And a circular 2D grid is generating using SnappyXMesh. At the end, we rotate the profile mesh according to the angle of attack, and the overall mesh is finally assembled. In 2D, we have a 2 million cells mesh. Regarding the aerodynamic simulation, we are using the simple foam solver and the K-omega SST turbulence model. At the end, we get the aerodynamic coefficient Cx, Cy, Cmz, and we can plot the velocity field and the pressure field, as you can see in the bottom right of this slide. Then we developed a 3D workflow. So we created a fully automated setup with OpenFOAM commands. The ocean wings are oriented, and the mesh is done with Napier mesh. As we are in three dimensions, we have a wind gradient in velocity and angle, so it has to be taken into account in the boundary conditions. The simulation lasts around 4,000 iterations, and the convergence is checked with the monitoring of the aerodynamics coefficient of each ocean mix. Finally, the post-processing gives images of velocity, pressure, and streamlines. As a first proof of success of this project, I would like to show that thanks to this work, AYRO is able to easily adapt the workflows to different configurations of ocean wings and new ships. You can see on the left 2D simulation of 6 ocean wings, and on the right 8 wings, ocean wings on a container ship. Now the HPC. So why we need why HPC is needed? So HPC systems offer high computational power and scalability, enabling faster and parallel processing of complex simulation. By reducing processing time and handling large workloads, HPC systems significantly improve efficiency and accelerate research and innovation. So what we did, so we create several workflows, and we developed a robust tool consisting of a command line interface, enabling the automation of OpenFOAM CFD simulation on HPC systems. It significantly reduces cost and times. So how? So the submission process is fully automating using a simple CSV file containing the parameters. And at the end, the results are saved in a downloadable zip file containing images and CSV files for easy access and analysis. We, in this project, we decided to not save any CFD data because of the size of each runs, and it's very easy to rerun a selected simulation if we need to go further in the post-processing. During this project, we did over 6,000 2D runs. So just to give you an idea, one 2D run takes 40 CPU hours, and we did around 150 3D runs for a total of 350 CPU hours. All of this data all of the data produced are the inputs of the optimization part. And about optimization, I let Marco continue. Marco?
Yes.
Yes.
Good morning, everyone. I'm Marco Zanichelli, engineer at Toolspot, and I will start by presenting the work developed by USI. So at USI, they developed a surrogate modeling technique based on a novel multi-resolution kernel methods. This surrogate modeling method is explainable, versatile, efficient, and scalable. This kind of surrogate model has two main outputs, mean and standard deviation. The mean is the approximation of the input data, and the standard deviation is an indication of the model's inaccuracy. In this case, the input data is represented by 2D CFD calculations. In the figure at the right, the red points are the prediction of the model. The blue lines represent the standard deviation, and the green points represent the actual values of the CFD dataset. Mean and standard deviation are crucial in the definition of a Bayesian optimization procedure. Can you? Okay, thank you. Bayesian optimization is a process that allows user to prioritize either the accuracy of the surrogate model or the speed of reaching the objective's optimum. This is achieved by selecting an appropriate acquisition function. This figure illustrates the model prediction based on the available observation and the indication of the model's inaccuracy represented by the standard deviation. The model prediction is the dashed line at the top, and the inaccuracy is the light blue area. Through iterative additions of new observations, the Gaussian process is updated. In this way, the standard deviation decreases, resulting in an improved surrogate model. The bottom part of the figure displays the value of the acquisition function across the domain. This function balances the trade-off between enhancing the model's accuracy and targeting the objective of the problem. The maximum value of the acquisition function determines the next point to be run in CFD, completing in this way one iteration of the Bayesian optimization loop. So, thank you. In this slide, you can see how Bayesian optimization is created using the user interface of Breva, which is the software we are developing at Toolspot. Since online calls to the CFD solver were outside of the scope of the project, a modified approach was adopted for Bayesian optimization. Initially, an exploration of the design space was conducted by performing a comprehensive full factorial sampling. These samples were used to build a multilinear response surface that you can see in the left part of this figure. This multilinear response surface served as a surrogate for the CFD solver in order to develop a full Bayesian optimization process. In the left part of the figure, you can see where the initial dataset for the Bayesian optimization is generated through latent hypercube sampling. Then, after having generated this initial dataset, the main Bayesian optimization loop is created. Initially, we train the Gaussian process on the latent hypercube data, and then we optimized this Gaussian process according to the acquisition function. This optimization returns the next point to be ran or to be evaluated, in this case by the multilinear response surface. And once we have the value of the outputs of the multilinear response surface, we just need to update the dataset and retrain the Gaussian process. And so this loop at the right is run until some convergence criteria are met. Here instead, you can see the results of a Bayesian optimization performed in Breva. The gray points here represent the full factorial CFD dataset that was used to generate the multilinear response surface. Here on the plot, the x-axis represents the x component of the aerodynamic force on the ship, whereas the y-axis represents the y component of the aerodynamic force on the y-axis of the ship. This gray dataset is not directly used in the Bayesian optimization, but is just used to generate the multilinear response surface. The Bayesian optimization data is represented here in green, which is the initial latent hypercube sampling, and in blue, which are the Bayesian optimization steps. In this case, the optimization objective is the maximization of the x component of the aerodynamic force. And as you can see, in the main optimization loop, we have some points that are in the middle of this plot, but this process rapidly moves towards the problem optimum. This is another post-processing plot that is available in Breva. It is the parallel plot. With this plot, we can see together both inputs in the first 4 columns and outputs in the last 2 columns. By restricting the values of the objective function as done here in figure, it is possible to have insights into the values of the inputs that generate points that are near the optimum. In this way, this allows the user to have a better understanding of the problem, understanding which values are important, which values of the inputs are important in the generation of a high performance output. Thanks to this project, we had the chance to test these innovative algorithms on an industry relevant problem. And I think the results show that these processes are suitable for this kind of experiments. Thank you.
Thank you, Marco. So I will continue with the major achievements. So the collaboration between AYRO, Polimi, Cineca, ToolsPols, and UC results in a comprehensive solution for the design, simulation, and optimization of the ocean wing systems. The improved HPC capabilities for faster simulation and optimization support complex analysis and design exploration. The affordability and scalability of the developed solution empowered AYRO with an efficient workflow, enhanced optimization capabilities, and the ability to feed the AI-based wing control software for improved performance. We have also a customizable workflow editor for Bayesian optimization, simplifying optimization processes and enhancing design efficiency. And finally, the Gaussian process modeling integration into Breva software, enabling faster evaluation of design alternatives and informed decision making. The expecting impact of the solution. So first, on the business side. Sorry. So we have optimized the WAF system, and with a customizable workflow editor, we can enhance competitiveness. The cost savings improve market positioning and competitive advantage. About the business benefits, so AYRO can expect an additional 300,000 in annual turnover by selling improved control software to existing clients and the client portfolio, which is 200 installed ocean wings. The creation of HPC-backed wing control software for any vessel type will enhance competitiveness on all ship types and open up new markets. There is a projected 300 increase in wing sales related turnover until 2030. For ToolsPols, ToolsPols can leverage improved technology tool chains to increase sales by up to 40,000 annually. And finally, for Cineca, could gain additional business as an HPC supplier, generating approximately 20,000 euros per year. So it drives innovation, technological advancements, and economic growth.
Okay, thank you very much. So, good morning. My name is Dimitris Lampropoulos, and I'm here to represent both FEC Engineering PC and UNIS Wind SA. Our experiment is called GEMINI, or high fidelity modeling for a small wind turbine. So let me give you a brief of our outline. First of all, I will present a general challenge of our problem, then our tools, which mainly is the CFD part, then some of our results, and then the main benefits of this experiment. So first of all, let me address why all this was necessary, because in recent years there has been a significant increase in environmental concerns across the globe, as you may know. People are becoming more and more aware of the impact of human activities on the environment, and are actively seeking ways to mitigate these effects. So this growing consciousness has led to a greater emphasis on environmental care in various sectors, including energy production and consumption. So one of the key objectives in environmental care is the reduction of pollutants such as nitrous oxide or CO2 and other emissions that contribute to air pollution and climate change. So industries and individuals alike are recognized the importance of lowering these emissions to safeguard human health and preserve the planet's natural resources. So another aspect closely related to the environmental care is the need to decrease noise levels associated with industrial activities and infrastructure. So noise pollution has been linked to various health issues and can have a negative impact on both humans and wildlife. Furthermore, there is a growing need for higher efficiency in energy production and consumption. With the increasing demand for energy, it is crucial to maximize the utilization of available resources and minimize energy waste. So this involves the development and implementation of innovative technologies and practices that improve energy efficiency across various sectors, ranging from transportation to manufacturing. Additionally, the desire to keep installation alive for a longer time has become a prominent factor in decision-making processes. Rather than opting for short-term solutions, there is a focus on developing infrastructure and systems that are durable and can withstand the test of time. This approach not only reduces the environmental impact associated with frequent replacements, but also contributes to long-term sustainability. Moreover, the limitation of maintenance cost is a critical consideration in many industries. High maintenance cost can be financially burdensome and can also contribute to increased environmental impacts. By implementing strategies that minimize maintenance requirements and optimize the lifespan of equipment and infrastructure, both economic and environmental benefits can be achieved. Furthermore, the rise in intermittent power generations, such as renewable energy sources, has highlighted the importance of energy storage. Peaks in energy demand can strain the power grid, while intermittent generations from renewable sources may not always align with demand patterns. So overall, these aspects, including increased environmental concerns, environmental care, lowering pollutants, decreasing noise levels, and the need for higher efficiency, keeping installation alive for a longer time, limiting maintenance costs, and addressing peaks in energy demand, are driving forces in shaping our approach towards a more sustainable and environmentally friendly future. So by addressing these factors, we can strive to create a world that is greener, cleaner, and more resilient for generations to come. So in line with the increasing focus on environmental concerns, as I mentioned before, and the need for high efficiency, and taking into consideration the European initiative called FF4EuroHPC, we have been launched to examine a small, so let me address this, that the Euro FF4EuroHPC provides small and medium-sized enterprises high access to high performance computing HPC centers related technologies. So this initiative aimed to harness the power of HPC systems and simulations to drive innovation and sustainability in various industries. So as a part of the FF4EuroHPC, we have conducted a novel experiment that has been designed to demonstrate the benefits of high fidelity computational fluid dynamics, or CFD, simulations for small wind turbines. The objective of the experiment is to showcase how HPC technologies can enhance the design and performance optimization of these turbines, ultimately leading to a more efficient and environmentally friendly wind energy generations. So several key partners have joined the forces to carry on this experiment. As I mentioned before, the UNIS Wind SA, a renowned wind turbine manufacturer with a commitment to sustainability, brought its expertise in wind energy and turbine design, and also FEAC Engineer PC, an engineering consultancy firm specializing in computational simulations, contributed with its vast experience in CFD modeling. So together, the partner, us and the UNIS, form a strong foundation for the experiment, providing the necessary domain knowledge and technical skills. But also to enable the high fidelity simulations required for this experiment, the partnership has collaborated with IOTA Advanced Computing Company. So IOTA are based in Croatia, and it's a prominent HPC provider known for the very reliable HPC infrastructure. So the experiment involved creating accurate virtual models of these small wind turbines, capturing the intricate flow dynamics and interactions with the surrounding environment. So by employing high fidelity CFD simulations, the partners, we aim to gain a comprehensive understanding of the aerodynamic behavior, performance characteristics, and energy efficiency of the wind turbine under investigation. So the insights obtained from these simulations will serve as a valuable resource for optimizing turbine designs, enhancing their performance, and reducing their environmental impact overall. So through the collaborative efforts, the partners involved in this experience, we worked together on this experiment. So let me move to the next slide. So the wind turbine under testing is the EW1630, which is the benchmark product of Unis Wind. It's the first and only Greek wind turbine manufacturer, which is the first and only Greek wind turbine manufacturer. So the EW1630 is specifically designed to meet the needs of sustainable energy generation. It has a nominal power output of 50 kilowatts, and it also has a tower hub height of 22 meters, providing an optimal elevation for capturing wind current. So the rotor diameter spans 16 meters and allowing for a substantial swept area of 200 square meters. In terms of compliance, the EW1630 adheres the international standard IEC 61400-2 for Class 2 winds. So this standard sets criteria for the design and performance of wind turbines, taking into account wind conditions and their impact on turbine functionality. By meeting these standards, the EW1630 ensures the reliability, safety, and efficiency of its operations. So the selection of the EW1630 as the wind turbine under testing for the experiment demonstrates Unis's commitment to innovation and sustainability. So let me move to the next slide. So the experiment's initiative is driven by several key project goals. These goals encompass the further improvement of the turbine's design, increased energy yield, and the overall cost reduction. So the first goal of the project is, as I said before, is to achieve further improvements in the design of the EW1630 wind turbine through the high fidelity CFD simulations and the utilization of the HPC technologies. The partners aimed to gain the detailed insights into the turbine's aerodynamic performance and behavior. Also, increased energy yield is another crucial objective for this project. By fine-tuning the design and the operational parameters of the turbine, we aim to maximize its energy generation capabilities. In addition to design improvements and increased energy yield, the project also aimed to achieve an overall cost reduction. So by leveraging advanced computational tools and simulations, we aim that we can identify opportunities for cost optimizations throughout the turbine's life cycle. So, okay, let me move to the next slide. So the challenges. Small wind turbines encounter challenges arising from the turbulence-induced vibrations and complex flow patterns. So these factors can significantly impact their performance and overall efficiency. To address these challenges, the application of CFD simulations are crucial. However, it's important to note that the limitations are also associated with CFD and the turbulence modeling. So common practice when we examine turbulence modeling is to use tranche models. So they are widely used and they're a computationally efficient way, but may not capture the complex flow phenomena and turbulence characteristics experienced by a system like a small wind turbine. As a result, relying solely on tranche models may lead to inaccurate predictions and suboptimal design decisions. To overcome this limitation and achieve more accurate results, high-fidelity modeling techniques like detached edge simulations, DES, or large edge simulations, LES, are essential. These approaches provide a more detailed representation of the flow physics, enabling a better understanding of the turbulence and its interaction with turbine components. DES and LES models are particularly well suited for capturing the unsteady flow phenomena and all the turbulence structures. However, it is worth mentioning that employing this high fidelity modeling techniques requires enormous computing resources. These simulations are computationally demanding and typically require access to a powerful HPC system. So these systems are capable of handling the massive computational workload. So as you may understand, they're crucial. So by acknowledging these challenges posed by the turbulence-induced complex flow patterns, and by leveraging advanced modeling techniques such as DES, the project aimed to overcome these hurdles and gain deeper understanding of the flow dynamics through the utilization of an HPC system. So in a collaborative effort, we developed a sophisticated CFD model. The model was specifically designed and optimized the performance of the wind turbine on its actual operation site. We took into account the unique characteristics of the environmental conditions of the site. To conduct these simulations, we leveraged, as I said before, the IOTA HPC resources, and over 480,000 CPU hours were employed. During the simulation processes, detailed data on the wind turbines' operational performance under varying wind speeds was gathered. So this data collection adhered to the requirements set forth by the manufacturer, ensuring that the simulations are aligned with the real-world conditions. So by capturing the turbine's behavior in different wind conditions, we evaluated its performance, identified areas of improvement, and we tried to optimize the design accordingly. So the simulation process involved the utilization of pretty dense computational meshes with over 45 million cells. These meshes provided a high level of resolution, enabling a detailed representation of the flow physics and capturing of the complex physical phenomena occurring around the wind turbine. So the model and simulate this phenomenon accurately. The detached steady simulation method was employed. The DS combined the benefits of both Reynolds average Navier-Stokes and the large eddy simulations approaches, allowing for a more comprehensive understanding of the flow dynamics. So I haven't mentioned before, but in this project we used the SimCenter StarCSM Plus, which is a commercial CFD solver. Within SimCenter StarCSM Plus, the SSTK Omega detached steady simulation model was selected as the primary choice for simulating the flow dynamics around the wind turbine. The SSTK Omega model available in StarCSM Plus combines the strength of SSTK Omega simple runs model in the boundary layer with a large eddy simulation approach in unsteady separated regions. This unique combination enabled an accurate representation of both the mean flow behavior and the unsteady turbulent fluctuations that occur around the wind turbine. The DES formulations of the SSTK Omega model, a modification was applied to the dissipation term in the transport equation for the turbulent kinetic energy. This modification enhanced the accuracy and representation of the complex phenomena, as I mentioned before. By utilizing SimCenter StarCSM Plus and SSTK Omega, the project benefited from this powerful simulation platform that could accurately simulate all the intricate flow dynamics. So let me move to the next slide. So to validate the computational CFD, the computational fluid dynamics or CFD results, we had to make some sort of validations. So to do that, we created two different domains. The first domain consisted of a small area with flat terrain. This domain was specifically designed to validate, as I said before, the CFD results by comparing them with theoretical data provided by the manufacturer. So by simulating wind flow and turbine performance in a controlled environment, we aimed to verify the accuracy of our CFD simulation. But the main goal was to do simulation, CFD simulations, including the actual terrain and site where the turbine is. So in addition to that, we had to to construct a bigger domain that represents this complex surface. So a larger domain was created using satellite images to accurately represent the actual site where the turbine is located. So, and at this point, let me add something that I see is missing from the slide. Two domains were used for this kind of simulation. We have one large domain that contains the air around the wind turbine, and one smaller cylindrical shaped domain that contains the rotor and the blades. And this cylindrical domain is rotating around an axis that goes on the center of the hub of the turbine. So another important area that we have to mention is the boundary condition used for this kind of simulation. So as an inlet region of the computational domain, on the inlet region of the computational domain, we use the atmospheric boundary layer condition. So this condition represents the region close to the Earth's surface where the wind flow is influenced by surface characteristics such as vegetation and terrain features. So due to computational limitations, representing the exact ground roughness in the simulation becomes challenging. So to address this, a roughness model was also employed to approximate ground roughness in the atmospheric boundary layer. The roughness model took into account factors such as grass, trees, and other features that affect the velocity distribution near the ground. To make all the simulation possible, when we talk about CFD, computational mass is a crucial part. So all our computational masses were generated by StarCCM+. StarCCM+ offers three possible choices when it comes to computational masses. It offers polyhedral mesh, hexahedral mesh, and tetrahedral mesh. In our experiment, we use solely polyhedral meshes, and around all the surface of the wind turbine, we used 12 layers of boundary mesh to capture the boundary layer of the air. Also, due to the long blade, we took the decision to go with high Y plus approximation to keep the count of the computational meshes cells down. As I mentioned before, meshes that went up to 45 to 50 million cells were generated. So here we have some details of the validation, and we used the 6 different wind velocities: 3.5, 6.5, 10.5, 12.5, 14, and 15.5 meters per second. These wind velocities were chosen specifically by the manufacturer because there was a particular interest of how the turbine operates and performs. And as you can see on the right on the slide, you can see a theoretical power curve with blue and the calculated with power from our CFD. So we were amazed that we were too close to the actual result. And then we moved on to the actual complex terrain, with included the actual mountain that the wind turbine was located. So again, we examined 6 different wind velocities, and the main findings of these simulations were that when the wind turbine is located on that particular mountain, we have a local acceleration of the wind speed there. So as someone can understand, there is an early increase in the turbine's performance compared to the theoretical studies that the manufacturer has conducted. So subsequent decreases due to the blade stalling come much earlier compared again to the theoretical data. So as you can see here, the previous comment is obvious in this graph. With the green color is the power curve of the turbine located on the actual site on top of the mountain. So this knowledge aids the manufacturer maximizing energy output and improving the wind turbine's efficiency, and also ensure the long-term viability of wind energy projects regions characterized by diverse terrain features. Here are some indicative photos that you can see how the velocity contours of the velocity magnitudes and also turbulent intensity. Here is the front side of the wind turbine. And okay. And now let us go to the business impact. So first, the test efficiency. The adoption of HPC-based CFD simulation in this project had significantly reduced the need for extensive physical testing and measurement. That was very crucial for the manufacturing because logistics and all the paperwork that is needed to manufacture and then transfer the wind turbine in its actual site to make an experiment, it's extraordinary. So that was a huge step forward. Then comes cost saving by utilizing simulation instead of constructing new wind turbines solely for testing. As I mentioned before, Wind Turbine SA has realized that substantial cost savings can be done. So it is estimated that the company can save approximately 10 to 70% of the total expenses, equivalent to around 300,000 euros. So these cost savings contribute to the overall economic efficiency of the project and allows better allocations of resources towards other projects. Also, the R&D cost reductions, simulations play a crucial role in providing valuable insights and strategies for cost reduction and further development of the EW16 turbine. And also it gives the manufacturer a competitive advantage that the use of simulations, it's a very important advantage, and also enhance the expertise. So the collaboration with FEAC Engineering PC in this project has enabled them to gain valuable experience and expertise in high fidelity simulations using large scale HPC resources. So as FEAC Engineering PC, we had no prior experience working with large scale HPC resources. So that was a very insightful and helpful task for us. And also another very important aspect is the environmental sustainability. So the adoption of a novel HPC-based methodology in wind turbine design promotes environmental sustainability because by utilizing high fidelity simulations, the project aims to optimize the performance and of the wind turbine, reducing, as I said before, the need for physical testing and prototypes, which is minimizing waste from non-recycled materials, because a huge problem of wind turbine is that they cannot be recycled. So this approach aligns with principles of sustainable development by minimizing the overall environmental impact. And also another very important aspect is the project's objectives and outcomes are in line with the goals of the European Green Deal, and also the development of the advanced wind turbines models through this project has a positive social impact, as you may understand.
Thank you. So good morning to everybody. My name is Eduardo Perez and I'm a postdoctoral researcher at the Barcelona Supercomputing Center. And on behalf of my colleagues, I'm going to present the results of the H2 FEACOMP project in this work entitled HPC-based virtual platform for low emissions hydrogen-based technologies for industrial combustors. The simulations have been performed by Dr. Mira and our PhD student, Bruce Love. So I will start talking a bit about our center, then about our group, to jump into the context, motivation, state of the art, the importance of the multi-scales, the disparity of scales in this kind of simulations, and then to go into the results of the project and to conclude with an outlook. So we are the Barcelona Supercomputing Center. We are a Spanish National Supercomputing Center. We are located at the southwest of the city of Barcelona in the Polytechnic University of Catalonia. We are a total of 800 people, and we are divided into four departments. Our department is CASE, Computer Applications in Science and Engineering, and while BSc is very well known not only for its research, but also because it hosts Mare Nostrum 4, which
It's a supercomputer with 3.4 petaflops, and it's a very powerful supercomputer in Europe. And right now we are mounting a Mare Nostrum 5 that is one of the pre-scale supercomputers, and that will be available in the incoming months. So the department is divided in several groups. We are the Propulsion Technologies group, which is led by Dr. Mira. And our research activities are aligned with the European decarbonization strategy. We work mainly in the power generation and transportation sectors. So what we are specialized in high fidelity simulations of multi-physics systems with a focus on high performance computing and exascale enabling methodologies. Recently, we have started with data-driven methods and artificial intelligence. The applications that we deal with are propulsion and power generation. Traditionally, we have worked quite a lot in the aeronautical sector, and in the last years, we have expanded our research to hydrogen combustion, not only in propulsion, but also in furnaces, like in this project. And also, we have started recently a section of electromobility. So here, you can see the results of some simulations. They correspond, these are simulations that reproduce experiments from the literature. We have performed this with our in-house code ALIA. And well, from here, I would like to highlight three things. The first one is that we are focused on large eddy simulation, high fidelity simulations. So you can appreciate how in all the simulations, we are able to reproduce very small vertical structures. So that means that we are solving quite accurately the flow. Also, we deal with multi-physics. So we have radiation models, we have a transport of particles. Also, we can do a fluid-solid interaction. So we have a lot of physics in our code. And finally, we can deal with complex geometries, as you can observe here, what is appropriate for industrial combustors, and as we have deal with in this project. So because ALIA can work with as structure or unstructured meshes. So going into the context and motivation, well, the first thing is that hydrogen seems to play, well, it's playing right now a big role, and it's forecasted that its role is going to be much greater in the coming years. So here you can see a forecast of the market share, and you can observe that hydrogen will play a very important role in all the sectors, going from power generation, transport, until industry feedstock. So we think that it's very important to have accurate models that can reproduce a hydrogen combustion, to have reliable simulations that can aid in the design of the combustors. So going into the state of the art, well, the first question would be, can we simulate real industrial systems, or are we limited to lab scale combustion systems? Because in real industrial systems, we have a set of difficulties, of issues that can complicate quite a lot the resolution. In particular, we have complex geometries with very small details that can have an effect or an impact on the flow. We can also have multiple injectors that can interact between them. Also, we have a multi-physics, multi-scale phenomena. That means that both in spatial and temporal, we have a great disparity of scales. And also we can have multi-phase, so we can have on the one hand liquid phase and gas phase and even solid particles. Also we have turbulence and chemical reactions and radiation, and they are all strongly coupled in a non-linear way. And finally, the boundary conditions can play a very important role. So it's the real industrial system is very challenging, and it's not only that we need many layers of physics. It's also the problem comes from this multi-scale nature of the problem. So regarding, for example, the spatial scales, we have that the scales can range from very few millimeters, like the flame thickness or the fuel injector, to tens of meters, like the chamber length. And also in the temporal, something similar happens. If we consider acoustics, then we will be in the order of milliseconds, while we can have chemical species that are produced and consumed, like the hydroxide, in terms of in an order of magnitude of microseconds. And also regarding the NOx, the pollutants usually are slower. We can have that their production occurs in hundreds of milliseconds. So at the end, we have a great disparity of spatial and temporal scales, and this introduces a high complexity. And the question is, how can we solve this problem without incurring in a very high cost? So on one extreme, we have Reynolds average Navier-Stokes, which we have to rely all our physics on the models. So this is, I would say, this is quite challenging because the largest scales are very anisotropic in general. So they are very conditioned by, for example, the geometry of the domain. And this can introduce important errors. And in the other extreme, we have the direct numerical simulations, DNS, that for this distance is totally unfeasible. In between, we have an intermediate option that I would say is a very good trade-off between cost and accuracy, that is large eddy simulations. So in large eddy simulations, we solve the largest scales, but we still model the smaller scales, which tend to be more isotropic and therefore more susceptible to be properly modeled. But still, we need models, and they can introduce they have a big impact on results. So going into the physics of the combustor, here you have a very simplistic sketch of the combustor, and we can clearly distinguish two regions. One is the near flame region, where we have fast, very small time scales, very fast dynamics because of the flame, a lot of chemistry, and intense chemistry, and we can have instabilities. And also we have the post-flame region, where the time scales are much bigger. Everything happens in a much slower manner. Typically, is in this region where the emissions are produced. So it seems that it's natural that if we have different physical phenomena, we also apply different techniques to simulate this physics. So for the near flame region, it's quite convenient to use high fidelity models, like using based on large eddy simulations, because, as I say, we solve the largest scales. Also, it's very interesting the use of data-driven methods, so like proper orthogonal decomposition or dynamic mode decomposition. These techniques allows us to find let's say, the governing structures of the flow. So even this flow seems, and it really seems very, very complex. At the end, there are like some dimensions or variables that mainly explain or govern most of the phenomena that occur. These techniques allow us to find out which are these dimensions. Also, we can condensate the whole behavior of the system in terms, for example, of frequency in the flame transfer in the flame transfer function or the flame describing function, which help us to understand the instabilities as a function of the frequency. And finally, we have the machine learning assisted models, so we can fed a model with real data or large eddy simulation data, and with this generate a very cheap model to do calculations in a very fast way. And on the other hand, for the techniques for the post-flame region, we can use runs in this case, because the scales are slower, the disparity of the scales is smaller if they are properly calibrated. Also, it's very positive to use reduced order models. And finally, for the chemistry, a more simplistic way to treat this region is with reactor networks. So at the end, it seems that a good combination of physics-based and data-driven models allows us to solve the flow and to understand the underlying structures that explain the behavior of the flow. So this project, H2B-TCOM, that has been financed in the frame of FF4EuroHPC, is a collaboration between EM Combustion, which is a Spanish an SME Spanish SME that manufactures burners, and the Barcelona Supercomputing Center. And the purpose of the project was that in the plant of SEAT, which is the car manufacturer that is placed in Martorell in the province of Barcelona, during the stage of the painting, they issue an aerosol for the painting, and then there are particles of painting that are in the air and cannot be issued to the atmosphere. So they are burned in these burners that you can see here, but right now they are burning with natural gas. And in the path of the decarbonization of the Spanish industry, they want to switch to hydrogen with the burners manufactured by EN combustion. And the goal was to do this, the simulations with high fidelity simulations with our code to understand better how what are going to be the NOx emissions and the behavior of the flame. So, this is a cut of the burner. So you can see that the gas with the particles come through this heat exchanger, and then the particles are oxidated in the combustion chamber, and finally they are issued to the atmosphere. So one of the challenges in this case was that the burner is extremely large. We have 7 meters of length, while we have 8 meters of length and 3 meters of diameter. So compared to the scales of the flame, this is tremendously large. And the idea was how to let's say to look for a trade-off between accuracy and cost. Here you have a sketch of the burner. Clearly, there are many details that are not required for the flow simulation. So the cut was clean and simplified. And here you can see the inlet, the part of the inlet of the air with the blades. The shrill is very small, and the injectors. So in order to reduce the computational cost, what we do is to create a frustum where we have a very small element size. This is the region where the flame develops. So it's the region where we expect very small spatial scales and spatial and temporal scales, while in the rest, this is the post-flame region where the scales are much bigger. So this is in totally agreement with what I explained before. We make use of the physics, and we translate these time scales into the mesh to reduce computational time. At the end, the operational conditions are these burners have a thermal power of 1.5 megawatts. They work in an equivalence ratio around 0.8, 0.9. So we did the simulations with pure natural gas. In our case, we use methane and pure hydrogen to keeping the same thermal power. So you can observe that the mass flow rate for hydrogen is much smaller than for natural gas. This is because a specific energy density of hydrogen, that is per kilogram, is around 3 times that of the natural gas. But on the other hand, we have that the flow rate is much higher in the case of hydrogen, because in volumetric terms its energetic density is smaller. So this means that as we have higher flow rates, we are going to have higher velocities in the case of hydrogen, and this changes a bit the flow fields, the velocity fields. So talking a bit about our tool, we have used multiphysics code ALIA that we developed at the department. It's a finite element based computational mechanics code written in Fortran. And from the very beginning, a lot of attention has been devoted to high performance with parallelization. So we can use MPI, OpenMP, GPUs. So we can work with heterogeneous systems. And ALIA has been tested and up to 130K CPUs. Here you can see some strong scalability curves. So this means that in the ideal case, if we double the number of CPUs, we would like to double the speed. And you can see that in general, we obtain excellent performance for ALIA. Also, we have some dynamic load balance techniques, and currently we are working on mesh adaptivity. So it's a multi-physics code and can have, and also multi-code, we can have multi-code coupling. And I would say that it's a very powerful code. So this is another strong scalability curve obtained in HPC supercomputer, which is one of the most modern supercomputers in Europe, in Stuttgart. And you can observe that the scalability is almost perfect. So regarding the modeling approach, we use large eddy simulations, a flamelet based method, in particular the flame generated manifold, FGM. With a low max solver, we use explicit schemes with Runge-Kutta of third or fourth order, and low dissipation numerical schemes. And finally, we have this PyTorch interface to work with machine learning. So regarding the boundary conditions, at the end we have two circumferences where we inject the natural gas, either the natural gas or the hydrogen. So this inner circumference is to introduce the natural gas, while hydrogen is introduced through these injectors, but it can be introduced axially, also tangentially. And here it's hardly to see, we will see in the next slide, but there's another injector in this position for hydrogen. So this burner that was manufactured by Ion Combustion it has a lot of degrees of freedom and it's very flexible. So as I say, we can inject hydrogen through these holes in an axial manner, also through these holes and tangentially through these holes, while natural gas is introduced through these holes. And they can we can do the mixture that we prefer. They are controlled independently. So these are some snapshots for the instantaneous velocity and temperature fields. And well, I will talk a bit more in the next slides when I compare with natural gas, but you can observe that here we have very high velocities at the injection, and that we are resolving a lot of structures. You can see all the vertical structures. In this video, you can appreciate in a better way how these vortices develop. Maybe there is no as recirculation because the axial velocity is higher than the vertical velocity, but you can observe how these vortices break down, and the spatial scales are much bigger here than here. So we did a similar analysis for the methane flame, and comparing the results between natural gas and hydrogen, what we can observe is that in general the velocity fields are pretty similar. It's true that there are differences, appreciable differences here near the injection. This is in part caused because of the position of the injectors, and also because we have to inject hydrogen at much higher velocities than natural gas. The rest of the domain, the velocity fields are pretty similar. And regarding the flames are also pretty similar. The flame opening angle of the natural gas is a bit slightly larger than that for hydrogen because of these velocity fields. And I would say that the most important aspect is that we reach higher temperatures with hydrogen compared to natural gas. So we observe temperatures of 2,400 Kelvin in hydrogen, while in natural gas temperature may be in the 200 Kelvin lower. So this has a very important effect on the NOx emissions because they are very sensitive close to the stoichiometric, and at high temperatures they are very sensitive to the temperature. It is true that in the simulations were adiabatic, so no radiation was included, and this may have an impact on the maximum temperature and also on the emissions of NOx. So regarding the prediction of NOx, we have two methods. At the end, the FGM is the flame degenerate manifold. Basically, saves the structure of one-dimensional flames into a table, and we can tabulate either the concentration of the NOx or the source terms. So it's not clear which one is the best approach. They provide a slightly different fields, and this is still a work in progress that we are investigating. If we compare the NOx with hydrogen and with natural gas, we observe that, well, we appreciated much higher temperatures in the temperature in hydrogen, and coherently we observe higher concentrations for NOx in hydrogen. But as I say, this can be conditioned because we perform adiabatic simulations.
So thank you. So we have the topic solving ambitious challenges in high-end wastewater treatments using HPC and CFD simulations. So this project is a consortium of 2 end users and 2 companies which doing the contribution to the engineering simulation services. And furthermore, this project can be divided in 2 parts. The first is regarding to ozonation and the second into dissolved air flotation processes. So from my part, the company Hollinger and TK are working on ozonation, and Elkruch on the AYRO farm, which will be represented later by Erwin, is on the topic of dissolved air flotations. But we share the main objects, which are generating a standard digital prototype for high-end wastewater treatment, which are those in both cases. And also we want to expand the market shares and generate new marketplaces. So please the next slide. Okay. So from our point of view, talking about the ozonations, the main challenge is in the first place having a multi-phase, multi-physics model which is able to represent all the physics and chemical reactions which needs to be simulated. And in the next step, we need to look into the chemical model more deeply, which means we have to find a chemical model which fits, which makes it possible to simplify all the chemical reactions which are going on into a set of equations, which makes it possible to solve it for the hardware resources. And we also need calibration for that, since if you have a new model, you have to test it. And finally, we want to have our end users and ourselves to come an efficient workflow. So we have to integrate the simulation process into a simplified model. Yeah. So please the next slide. So what you see on the right side is a typical ozone reactor as we are going to simulate it, or as we do simulations on it. From the flow is going from right to the left. So we have wastewater inside, and there are ozone air mixture nozzles which bring in this ozone air mixture, and the ozone is in gas phase and is dissolving from this gas phase into the water, and in the water there is the reaction between ozone and this wastewater. It is in our past mostly organic compounds, so-called dissolved organic compounds, DOC. After this wastewater is activated by the ozone, it's leaving, and the wastewater is not cleaned. It's going to be cleaned by bacteria from a biological process on other steps. So the solution to come is first to create a simulation setup and look for functionality of these ozone reactors and the performance. And then we need to define this chemical model, and the idea is to go for the chemical model and the simulation setup separately and combine them, as you're gonna see on the next slide, please. So thank you. So we have divided in different sections. So the first thing is just concentrating on the multi-phase flow part, as we call it. So we have an air and water model. We look into the geometry of the ozone reactor. We have a look into the phases of air and water, into the turbulences and the dissolving processes. We parametrizing the geometry in order to be able to look into different geometries, doing mesh studies and so on. The second part is then the chemical model itself, and in there we're just regarding the chemistry in the water, and we're combining them into so we call it multi-physics model. Of course, the others are multi-physics models as well. You can regard it as a full model. So this is the combination, and using this model, we are able to do sensitivity analysis and optimizations. And at this point, the HPC approach is really important since we have two complicated physical and also chemical happenings going on, and therefore we need big hardware resources. And finally, we want to create something like a tool, having a setup which enables just having reduced parameters as input and go for a standardization optimization process for it. So please, the next slide. So thank you. So in here you see this multi-phase flow model. This is now a model without any chemistry. The water flow is from left to right, and in here you see the amount of air which is inside the water is dissolving. We do not resolve each particle by itself, each bubbles. Instead, we do have a model. It wouldn't be possible for computational costs to look into all the bubble sizes itself. Therefore, it's a standard model which is used in OpenFOAM for it. And yeah, can you go to the next slide, please? Thank you. Yes, and this slide is regarded to the chemical model we have. So we have a real simplified test model for it because the high computational costs are just for solving the chemical reactions in here. We try to go for as less equations which are possible. Luckily, we can do a really simple equation setup for it, which makes it possible to combine it with the multi-physics model. Because if we would solve all chemical reactions, this would hardly be possible. And on the right side, you see laboratory data, which we got from Hollinger, and we are in a really good agreement for that. Okay, and the pictures, yeah, that's fine, thank you. Okay, so in here I illustrate the combination of the chemical model and the multi-phase flow model to the multi-physics model, right? And the multi-physics model is now able to do simulations on the whole geometry, and also in respect to the chemistry which is inside. The ozone is injected by these nozzles and is dissolving from air phase to water phase, and in water it's reacting. And in here you see this wastewater which already has reacted with ozone. This step is about 10 minutes. So the whole the time that the water needs to go through to pass the ozone reactors is about 20 minutes, and we do have to simulate all these 20 minutes in a transient step in order to represent the full solution. So please, the next slide, please. Okay, and again I hear, no, this is too much. Yeah, thank you. Okay, and again in here I'm showing the same full model, the multi-phase physics model, but it's not representing the wastewater, which already has reacted, but it's representing the ozone concentration inside, since the ozone concentration is decreasing while the activated organic compounds are increasing. And doing these simulations, we had the advantage that in here our ozone reactor had really good symmetry conditions. So in real, this reactor has about a depth of 9 meters, but we only had to simulate 1 meter because of the symmetry conditions. And here it is about 3 meters, which we are doing. And in order to test this symmetry effects and to making sure that the symmetry conditions is okay to use. So, but in general for zone reactors, it's really important that we are able to simulate the chemistry as well as having a really big sized model, and therefore HPC is really really necessary in order to come up with these solutions. So the main outcome from our side is that we do have a workflow which works fast and efficient. We were able to do parametrizations and having our input parameters to simulate these ozone reactors. The results are in good agreement and the customers are satisfied with that. And this brings cost benefits to the customer as well as local improvements. And we are able to optimize our product by reducing, so the end user is able to optimize their product and offer a better product by reducing construction volume of concrete, and also lower the consumption of the ozone which is needed in the ozone reactor, which saves operating costs and is also for local reasons really important. And we are in an ongoing process to improve this standardized procedure which we already have. And at this point, I would give to Alvin. Yes, thank you, Alvin.
Thanks, Georg. So we move on because time is running. Let me start the full time. So we heard about ozonation. Now we switch to dissolved air flotation, which is quite similar except the chemicals, because we are dealing more with the kinetics. And the physics we've been evaluating is the volume of fluid approach. Then we are looking at several EMPs, Eulerian multi-phase. So we have a 2-phase liquid air, 3-phase solid liquid air. We're looking at granular pressure in the presence of particles. And we're looking at Eulerian multi-phase with a large-scale interface. So these were the approaches we did. And in terms of discretization, we were doing thin layer meshing, solution adaptive meshing. And we were using, for the time discretization, adaptive time step, because we are dealing with very small time steps and very big time steps. So this is an animation of the part of the component we are looking at. You see the piping and you see this spiral inlay for guiding the flow. So we see the flow coming in from down here, and then it's emerging into the spiral case until it reaches the inner part of that spiral. And then there, the flotation process is already that much developed that the foam or the particles in combination with the oxygen is moving up to the top, and it settles on top as a foam-like layer, which is taken out of the component then. And on the right-hand side, you see the first complete filling simulation we did after evaluating all the different kinds of models we need. So you can see the air coming in from here, and you can see it's emerging to the top. And in the following sequences, until the full filling of the tank, this layer is evolving to a all over the surface foam layer, and then it will be sucked off over here through that pipe. So the most challenging was looking at the models, and in this video we see a full filling cycle, and for this cycle it was enough to use the volume of fluid approach to simulate that, because it takes a lot of time, and we would have not been able to do that with high performance computing. So at the beginning of the project, we just used our own cluster with 128 CPUs, because it's enough for the model size, because the main impact on the simulation is from the physics and from the time step and from the solution adaptive meshing. So it does not give any benefit if we go to more than 128 processors. It would not scale efficiently. It would not scale that it's really worth to use it. So we had, especially because we had the same setup in our configuration with the CPUs, like the Hawk at the HLRS. So we have the same configuration, and so we could work with our own cluster. And the interesting part is now, because we will continue this project, because the customer is so convinced that we are on the right track, that we will go to a full parameterized simulation, and this we will do in collaboration with HLRS. I'm already doing jobs on the HLRS since 2000, and it's a very useful, very speed up way to run these high performance simulations. So we go here. The most interesting part in this project is the water and the residence time of the water. The longer the residence time, the better the purification process. And if we go from left to right, you see the residence time increasing, and you see that the biggest residence time really is, as it should be, is really in the center of the tank. And then when the clear water in the middle of the tank is taken out, you just have the foam up there, which has the longest residence time, and which goes out through this pipe after being concentrated on the top of the liquid surface. Then we extract the foam over here, and then the water is taken out from the middle of the spiral. To do verification and validation, it's really hard to do, because you need to create a transparent component of that tank and of the spiral case. And so we just took the lid off and looked into from the top. And what you see in white is this dissolved air flotation, where the very small air bubbles come in. I will start that again. Just let me move back. So at the beginning, you see the water, the wastewater coming here. At the beginning, the tank is filled with the water, with the wastewater, and then an additional wastewater is coming in from the bottom, filled with, or where injected air bubbles you can see in white. And these air bubbles then spread along the spiral case into the middle, and they evolve to the top of that spiral case. And as soon as the liquid layer reaches the top of the spiral case, then the foam is spreading out on top of the surface, and you can suck it off from the top, which is not there right now because we took the lid off. and the extraction pipe is connected to the lid. So the most interesting part of this project was to look at the flow distribution in the tank. And as you can see from left to right, we did a very good improvement, because the better the flow circulates with a high velocity component in the circumferential direction, and the slower the velocity is, the more is the buoyancy of the bubbles attaching to the particles and then lifting the particles to the top. In case of this, we had the outcome that VOF is most suitable for the transient filling process. So we split it up into different simulations. So we had the filling process, which takes a lot of time. And we looked at the full Eulerian multiphase with a population balance method for particles, because of the size distribution of the air bubbles. Because the air bubbles are of different size when they come in. You can't say that they are all having the same size, because they're attaching to each other, then they're splitting up. And so we did this injection of the air bubbles by a population balance method, and we did the exchange of mass between the oxygen and the solid particles by a coalitions model, which is still which was tested in a test case, and is transferred now to the full model. So the optimization, we had that first design from the customer, and the optimization still, because of the many parameters we have from the geometrical limitations, we have a lot of parameters to look into. And so it's definitely the case that this project will continue with the customer after, from now on, after finishing the EU project. And the design optimization to improve purity of the outgoing water will include additional parameters. So ratio of reactor diameter to height. That's one relation that we found out that is relevant for the optimization. The ratio of reactor diameter to the spiral sheet metal insert, the position and angle of wastewater and air inlets, the diameter of clean air outlet pipe, the reactor base and top cover geometry. That's also a significant input or significant optimization parameter. And this list can be continued to even the thickness of the spiral case and the channel width of the spiral casing. So it's a hell of parameters, a hell lot of parameters that can be inspected there. Concerning the business case, for us and our end users, it's relevant to expand market shares and to tap into new markets, and the new market will be the implementation of an additional cleaning stage in most of the European and Switzerland's wastewater treatment plants, because of the EU regulation from 2021, where there are set new standards to the cleanness of to the purity of wastewater. And this market, looking at all the wastewater plants in the industrial ones and the municipal ones, all over Europe and Switzerland, this will create a new market of about 2.7 to 3.7 billion euros a year. This is a number that's always making me dizzy. So it's hard to tell what in our case will be the benefit for the engineering SMEs, because we are a very small company. We think about 0.5 to 1 million a year, And the optimized cost-benefit relation for us will be about 20% of the usage of the HPC. And it will cut down our expenses and project turnaround times using HPC by around 30%. And this is really hard to estimate because it's a completely new market, and we do not know how the projects accelerate, how fast it will be driven by the EU, that all these wastewater treatment plants have to upgrade their systems. The most interesting point for us in societal influence is generating more and secure high qualified jobs, because this is a very specific physical problem, and you really have to have high experienced CFD engineers to work on these models. So for us, and I think I speak for TK as well, we expect about 1 to 2 employees per year more. We already hired a new person yesterday, so the engineer started yesterday. And the overall social aspect is supply population with clean drinking water and reduce the risk of antibiotic resistances, because we looked at very serious studies of the development of antibiotic resistances because of pharmaceuticals in the drinking water. Environmentally, it will mean that we reduce pharmaceutical pollution and as well micropollutions and microplastics in the global water resources. So that's a very, very important thing. And last not least, with this, I want to thank you.
Hello everyone, I am João Vidal. I work at Soprefa. I will be presenting the experiment high performance computing for extrusion, so for profile extrusion. This presentation I will start by giving you the objectives of the work. I will present you the team, the problem that we solved, the approach we took, the code development, and the solution impact. The objective of this work was to deploy a computational framework to support design and optimization of profile extrusion dies. This framework should run efficiently on HPC, and it should reduce development costs and time to market of, in this case, Soprefa products. Just for your knowledge, previous to this project, we were having 2 to 3 months of time to market. We expected to have 5 to 10 experimental tries, and we spent more or less 1 ton of raw materials just in trials. It would account for more or less 12 to 15K in development cost. That just for medium complex profiles. For higher complex profiles, it will be more. The team in this work, there was 3 organizations involved: Soprefa, Wolf Dynamics, and the University of Minsk. I will talk a little bit about the persons involved now. In University of Minsk, we have Miguel Nobre, it was the coordinator. We have 2 researchers, one at the beginning of the project and another in the end. Abhishek was in the beginning of this project, and Marta Oliveira in the end. And the HPC expert was Ricardo Vilaça. On the side of Wolf Dynamics, we have Georg Scheger. It was our optimization expert. And in the side of Soprefa, we have Alberto Sacramento. It was the manager that coordinated all the works inside here. We have Luis Ferreira. It's our extrusion expert. It was the guy that helped us in the experiments in the line. José Moraes was the guy that was scheduling and be sure that we have machines available. And me was I was making the simulations, part of the integration with the OpenFOAM. SOPREF, it was founded in 1972. It have more or less 50 workers, and it's located in Mosteiro, Santa Maria da Feira, Portugal. SOPREF have two main fields, shoe components and plastic extrusion. This work were performed in the department of plastic extrusion, and plastic extrusion have three main markets: swimming pool covers with our brand SafeSwim, composite deck with our brand TwinWound, and we also produce custom plastic profiles. The problem that we in SOPREF face, and mainly all the field of extrusion face, is that to produce profiles with the required thickness and shape as the market expect, we need to have balanced flow. There is a problem in this field that it's not easy to develop a tool that at first trial it's already balanced. As you can see in the first picture, this is the unbalanced flow. This would not provide us a good product. So we need to predict this. When with the tools that we already have, with the CFD, we are able to predict these flows. As you can see here, we have a high velocity in the top, and it is what we get in the video, in the experiment. And after this was optimization, we have the average velocity balanced, and you are getting we are getting here a balanced flow, and we are getting the right product. So after with this, we need to improve to implement HPC faster way to optimize these tools. So the main tasks in this project was to code development, code integration, porting it to HPC, and then we did some case studies. This approach have three main parts. It's simulation code, optimizing the CAD software. For simulation code, we use OpenFOAM. All the three organizations in this project have experiment with OpenFOAM, and it's open source software. We are able to customize the solvers as we want. For CAD software, we use Onshape and Fusion 360. Onshape because it runs on cloud, and it's not OS specific. We don't need to have Windows, Linux. It's any OS you can use it. And we also use Fusion 360. The Fusion 360 because it's the software that in SOPREF we have expertise. We are using Fusion 360 some time ago, and is the software that we use here. And as optimizer, we use Dakota. That was the software that Wolf Dynamics was working with, and Wolf Dynamics have great expertise on it. So on the part of OpenFOAM, as I already told you, it's easy to implement new solvers and to customize it. We implement a new solver. We call it HPC-4EuroHPC. This solver solves the energy equation, and we also added a temperature and shear rate dependent viscosity to solve our specific problem. To evaluate the results, we needed to create the objective function. This objective function works by calculating the flow rate on each section, and this chi is the flow rate, and for each section we calculate it. Then we have a global flow rate target, and we should minimize this objective function. After developing the code, we evolved to testing it to check if we were having the expected results. We use the industrial case that we already from SOPREFA. This is the swimming pool cover geometry, and we divide the outlet in many sections, and we run the simulations, and the results show what we expected. It proved that we were able to simulate these problems. So after that, we analyzed the convergence and the evolution of residual and the evolution of the objective function, and we realized that if we stop the simulation by the objective function value, we would save up to 50% in the simulation time. So what we did, we further developed the solver to stop by the objective function. Okay, so after this, we start porting and integrating the code. With OnShape, it was very straightforward process. The optimization with the OnShape start by manually launching by parameterizing the geometry on OnShape, then launching the Dakota script in the HPC, and everything would run automatically. Dakota would generate the new geometry parameters. It would update the script that generate the geometry. Dakota OnShape would update geometry and send back STL files. Dakota would one more time launch OpenFOAM, run the mesh and the simulation, and would read the results and would run up to the object, the required results. With the Fusion 360, it wasn't that straightforward. We needed to develop more tools. We needed to create a script that runs on Fusion API to export the geometries automatically. We also developed another script to run in Ubuntu WSL to transfer the files to the cluster. And we added Nextcloud because the HPC cluster wouldn't let us to RAID the hard drive many times because it would create a big overhead. The process here of optimization would start as the same as OnShape. We need to design the tool and parameterize it. Then we would need to launch manually the scripts, Fusion 360 script, the bash script to sync with the cluster, and we need to launch the Dakota script. From the part of Dakota would create the working directories and start giving new parameters for Fusion to generate geometries. After that, it would send a start file that Fusion would read. This start file is a trigger for Fusion to know that it needs to generate new geometries. After all of that, geometry is updated, and it sends the files to Nextcloud, and this script here that runs on WSL will wait for a transfer file, and when it knows that it's there, it sends the files to the cluster. In the cluster, Dakota is waiting for a trigger to start running the simulations, and this would go on and on up to the convergence of the optimization. After this, we also performed the scalability study. we calculated the time needed to perform 512 runs. This would be in an ideal case, because the optimization algorithm that we use runs, it depends on the number of variables that we are using. And if we use one variable, we would be able to run 512 runs at the same time, no, 32 runs at the same time. But as we don't have only one variable, in some cases we have 14, we were only able to run 14 simulations at the same time. And if no, we were able to run 14 simulations at the same time, that's it. And because of that, when we are preparing the simulations and the runs, we need to look at this table and check what is more close to the real case that we are simulating now. Now, the results. We performed simulations and optimizations for 4 cases. We were able to get improvements on the CFD part. As you can see, now we are able to run many trials. To make this amount of trials, it was not possible to do in less than a day. And now we are doing it in 15 hours, 19 hours, 23 hours. We are able to have really high number of trials right now, and the cost it's quite low. So after the simulations, we passed to the trials. We were only able to simulate, to run on the experiment 2 cases, because we didn't have time because of the machining time. There was some delays also on the porting of Fusion 360. We were able to run these 2. I'm going to show the video here. Okay. As you can see here, this is the P2 profile. It was the best result we have, and this is also the P3 profile. The results look like the ones we in the simulations. One thing that we didn't get, it's here in the P2. We got a really good profile. Just needing for we expect to have big savings on this one. And the P3, there are something that we don't understand, like the profile is symmetric, but the result wasn't symmetric. We are still investigating this problem, but we believe that the problem is not related with simulation, because if the simulation is symmetric, and there is no reason for the result not be symmetric. Maybe we are trying to figure out what was the problem. Maybe some problem with the homogeneity of the polymer. This is a thing that we still trying to figure out. Solution impact. We were able with this project to develop a workflow that help us to reduce the number of trials in 40%. And also to reduce the tool design cost. This accounts for more or less 4.2K savings per tool. In the end of a year, as we are producing more 15 tools per year, it would account for 20% in savings. Solution impact. For Soprefa, we expect to have a reduction of product time to market in the range of 30 to 40%. We expect to to reduce the consumption of raw material in trials in 40%. And there are two other impacts that we expect to have is like we will be more independent to external suppliers, and we will increase our the protection of our know-how. In the part of technical achievements, we achieved the reduction of simulation time by 50% by implementing the convergence by objective function. We were able to implement a workflow that perform a full optimization of a complex profile in the time frame of 1 day. We illustrate the capability to perform and search for an optimal solution without any user intervention after the parameterization of the carbon. And we are now able to perform optimization in CAD software that does not run on HPC environment. Thank you.